So welcome back. We'll be introducing inverse trigonometric functions for derivatives and integrals today. So the objective is just to derive and integrate inverse trigonometric functions, which I'm going to start with proofs for. So we'll do the derivatives first, then talk about the integrals and how to work backwards. Okay, so I'm starting with my attempt to derive the inverse sine of x. So if I wanted to derive the inverse sine of x, by definition of an inverse function, if I take the inverse sine of 1/2, what I'm really asking is what angle would I have to take the sine of in order to get 1/2? So in this case, an answer could be pi 6, because the sine of pi 6 is 1/2. So the first thing I can do is take the sine of both sides of my equation. If I do, I'll get the sine of y equals x, because the sine and the arcsine will cancel. So my first step, take the sine of both sides. I guess just do this with audio. Okay, first step, take the sine of both sides. Then I can derive that from both sides implicitly. So if I derive sine of y, I'll get the cosine of y dy with chain rule. If I derive x, I'll get dx with chain rule. And then because cosine y equals adjacent over hypotenuse, we could set up a relationship then. So this is the cosine of some angle y equals adjacent over hypotenuse. So I've got my hypotenuse, which would be 1, and my adjacent side, which we don't know. So we can use that to start solving for it. If the sine of y is equal to x, then that means my opposite side must be x, and my hypotenuse must be 1 for a triangle, right triangle relationship, that has an angle of y. Okay, so that'll allow me to substitute. Using Pythagorean's theorem, this side we don't know. C squared plus x squared should equal 1 squared. Or I could say c squared equals 1 minus x squared. Therefore, c is the square root of 1 minus x. Okay, which gives me my adjacent side here for c. So now I can substitute. The cosine of y is the adjacent over hypotenuse, so that's root 1 minus x squared over 1. Cosine y is root 1 minus x squared over 1. Okay, so I've got root 1 minus x squared dy equals dx. So if I want to solve for dy dx, the derivative of the original function, I could say dy is equal to dx over root 1 minus x squared. Or dy over dx equals 1 over root 1 minus x squared. Okay, with chain rule, I would multiply by dx. Therefore, the derivative of arcsine of x is dx over root 1 minus x squared. Okay, so I'd done something that you might not have seen before there. with that substitution in a right triangle relationship. Is there any questions on what we did? Okay, can you guys still hear me? Okay, cool. So next one, same idea. I'm going to derive the arctangent. So if I derive the arctangent, my first step is to take the tangent of both sides. So if I do, that'll leave me with the tangent of y equals x. Okay, then I can derive both sides. If I derive the tangent of y, I'll get secant squared y dy equals dx. Okay, if the tangent of y equals x over 1, and that means since tangent is opposite over adjacent, the tangent of some angle y equals x over 1. So my opposite side for this triangle should be x, and my adjacent side for this triangle should be 1 if my angle is y. Okay, then I can solve for the missing side using Pythagorean's theorem again, or 1 squared plus x squared equals c squared, where c is my hypotenuse this time. Therefore, c is the square root of 1 plus x squared. Okay, if I wanted to get the secant, my secant would be hypotenuse over adjacent. So that would be root 1 plus x squared over 1, hypotenuse over adjacent. So if I substitute, that would be root 1 plus x squared, squared, because this was secant squared y, times dy equals dx. Okay, if I want to solve for dy then, I can divide both sides by root 1 plus x squared squared. The squared and the square root can cancel, which will leave me with just 1 plus x squared. So my derivative of y is dx over 1 plus x squared. Therefore, the derivative of arctangent is derivative of arctangent x is dx over 1 plus x squared. Okay, again, lots of substitutions. Any questions on what we did? Okay, last one. Secant. Same first step. If y is equal to the arcsecant of x, make a side note here really quick. The arcsecant of x is another way of saying inverse secant of x. I don't care which one that you use. In newer textbooks, you'll see this one, arcsecant, and that's because they don't want you to confuse this with sine x raised to the negative 1 power, which would be written the same way normally. But if you see sine raised to the negative 1 of x, you can assume that they're talking about an inverse sine function, not sine x raised to the negative 1 power. If you want to raise sine x to the negative 1 power, you'll see this for the same reason. They don't want you to mistake it with an inverse sine. This is kind of an exception to our normal power rule, where sine y of x would be the same thing as the sine of x raised to the y power. We've got an exception for negative 1 just because our notation for inverse sine already uses negative 1. Okay, but to avoid that confusion, newer textbooks use arcsecant. However, a lot of times, if you've got a good professor in college, they'll use older textbooks to save you money. So I need you to be familiar with both ways, just in case. But if I say arcsecant, I mean inverse secant. It means the same thing. So in order to get rid of this arcsecant, I'm going to take the secant of both sides. So if I do, when I derive secant, I'll get secant y tangent y dy with chain rule equals dx. If I set up my right triangle relationship based on this triangle, the secant of y equals x over 1. Secant is the opposite of cosine. So this is cosine is adjacent over hypotenuse. My secant will flip that, so it'll be hypotenuse over adjacent. So my hypotenuse needs to be x, and my adjacent side needs to be 1 if my angle is y. To make this relationship true. And again, we can use Pythagorean's theorem to solve for our missing side length here. So c squared plus 1, since the side length not a hypotenuse, is equal to x squared, or x squared minus 1 underneath the square root is equal to c for our missing side. Okay, that will allow us to sub in for secant and tangent. The secant of y then is x over 1, or x. The tangent of y then is opposite over adjacent. So this will be opposite root x squared minus 1 divided by my adjacent, which is 1. Okay, so that'll allow us to substitute. Anytime I see a secant y, I can replace it with x. Anytime I see a tangent y, I can replace it with root x squared minus 1. Okay, so after we make that substitution, we're left with this. If I solve for dy, I'll get dx over x root x squared minus 1. So we can say that, since dy is the derivative of our original y value, which was way back at the first step, dy was the derivative of our original y, we could say that the derivative of arcsecant is dx over x root x squared minus 1. Okay, that's the longest proof for today. Any questions on this one? Okay, so that leaves us with 3 rules. For derivatives, the derivative of the arcsine of x derivative for arctangent of x, derivative for arcsecant of x. Okay, for our 3 derivative rules. Okay, I'm going to reorder this one just so I match the Word document. I'm double checking me on this one. I'm not changing anything. This was, I wrote x squared plus 1. I'm going to write 1 plus x squared just so I match the same way that I wrote it on the other file. Okay, so what that means is, working backwards, if I wanted to integrate, the integral of dx over root 1 minus x squared should equal arcsine of x. The integral of dx over 1 plus x squared should equal arctangent of x. And the integral of dx over x root x squared minus 1 should equal arcsecant of x. Again, just working backwards. We can even throw a little bit of a curveball here to see what happens if we've got a constant instead of one, which would give us 3 more new rules. I'll prove one of them working backwards just to show you that this works. So starting with 1 over a times the arctangent of u over a plus c. 1 over a is a constant. I'll actually just use my derivative rules here. 1 over a is a constant, so that will stay the same. If I derive the arctangent of x, we said we should get dx over 1 plus x squared. That dx would be the derivative of u over a. That's 1 over a times u, which would give me 1 over a. Okay, and then this x is my inside part, which was u over a. So if we simplify, this will be 1 over a times that 1 over a I'm going to move down, so this is du on top of a times 1 plus u squared over a squared. Would give me one over a times du over a plus u squared over a, and then if I multiply this into the bottom, that'll give me du over a squared plus u squared. Okay, so working backwards with constants will allow us to do this even if we don't have one exactly in this place. So if we've got any other constant a, we'll be able to integrate. Okay, so I'll go back to our PowerPoint and we'll update this then. So if I wanted to integrate, this would give me this. Okay, if I wanted to integrate du over root a minus u squared, I would get the arc sine of u over a plus c. If I wanted to integrate du over a squared plus u squared, I would get 1 over a times the arctangent of u over a plus c. And then if I integrate du over, u not x, u root u squared minus a squared, I would get 1 over a times the arcsecant of u over a plus c. Okay, gives us the last rules we need for integration for, I believe, for the rest of the year. Any questions on our rules? Okay. And I've got proof of all of these in the Word document if you want to go back. So I'm going to do a couple derivative problems and a couple integral problems as fast as I can. Since we're already a little bit over time, I think I'll just work them out. And if you guys have questions, please stop me. So if I want to differentiate arc sine of 2x to the fifth power, that's the arc sine of u. So if I derive it, I'll get du over square root 1 minus u squared. So my derivative of u, the inside function, would be 10x to the fourth power. That's my chain rule part. My inside part is 2x to the fifth power. So I'm going to see which one matches. Okay, so this one's got the right du, but we did not square our inside part. So not C. This one's got my right du. I did square the inside part, but I don't have a square root. So not D. This one just derived sine instead of arc sine. So not B. So here we are. Du on top. And then root 1 minus u squared. Okay, we'll do another. So what we've got here is really a double chain rule. I've got the square root of something, where my something is arctangent of 4x to the fourth power. So the first thing I'm going to do is define u. Our inside part u is equal to the arctangent of 4x to the fourth power. So that means y is equal to the square root of u, or u to the 1/2 power. So if I derive this, y equals u to the 1/2, I'll get y prime is equal to 1/2 u to the negative 1/2 power du, where u is the arctangent of 4x to the fourth power, and therefore my derivative of u would be 16x to the third power dx over 1 plus our inside part, 4x to the fourth power squared. Okay, so then we can substitute u for u, du for du, meaning y prime will now be equal to, got 1/2 means my 2 will be on bottom. U to the negative 1/2 power means I can move that u to the bottom. So this is the square root of my original u, which was the arctangent of 4x to the fourth power. Okay, times my du, which is times this part, will be times 16x cubed dx over 1 plus 4x to the fourth power squared. Okay, if I'm dividing by a fraction, I can flip and multiply. So if I divide 16x cubed dx, 16x cubed dx divided by 1 plus 16x to the 8th power. Okay, so I divide that fraction by 2 root arctangent 4x to the fourth power over 1. I can flip that last fraction to become 1 over 2 root arctangent of 4x. And then we'll just need to match. Okay, I do have a little bit of simplifying I can still do, where 16 goes into 2 8 times. But other than that, I think that's about all we can do. So that gives us y prime is equal to 8x cubed dx on top, over 1 plus 16 x to the 8th power, all times the square root of arctangent 4x to the 4th power. Okay, and then we just need to match. So this first one has an arctangent on top, so it cannot be A. This second one also has an arctangent on top, so it can't be B. This third one looks really close. We've got everything we need on the bottom, but I've got a 16x cubed on top instead of an 8, so they did not divide by the 2. So not C, which leaves me with D. That's 8x cubed, which is what I have on top, 8x cubed dx, over arctangent 4x to the 4th power times 16x to the 8th plus 1. Ooh. Let's do this one for number 7. If I want to derive this, my derivative would be, so this is the arcsecant of u, so I'll get du over u root u squared minus 1, where u is x cubed plus 4 to the 1/4 power. So that means du would be equal to, okay, I'm going to write down here, I think, because I've got this mess over here. Du is equal to 1/4 x cubed plus 4 to the negative 3/4 power, that's 1/4 minus 1, times 3x squared dx. And then we can substitute. So my final answer should look like this. Y prime is 1/4 x cubed plus 4 to the negative 3/4 power times 3x squared dx divided by x cubed plus 4 to the positive 1/4 power square root x cubed plus 4 to the 2/4 power minus 1. Okay, then we can simplify. Okay, this 1/4, I can move that 4 to the bottom. This is x cubed plus 4 to the negative 3/4. If I move that to the bottom, this will be x cubed plus 4 to the 3/4 times x cubed plus 4 to the 1/4. If I'm multiplying, I can add the exponents together. So that'll give me times x cubed plus 4 to the 1st power, 4 over 4. The 3x squared dx can stay on top, 3x squared dx, times the square root of x cubed plus 4 to the 2/4 power is 1/2. Minus 1. Any questions on this one? Okay, so that's good for derivatives. For integration, we'll be working backwards. So this is in the form of arcsine. Since the integral of dx over root a squared minus x squared is equal to the arcsine of x over a plus c. Right now my a is 1, and x is just x. So this is the arcsine of x over 1 plus c, or the arcsine of x plus c. Okay, here the integral of dx over x root x squared minus a squared is equal to 1 over a arcsecant of x over a plus c. Okay, for us, our x is t and my a is 2 right now, since this is a squared. So that would give me 1 over a, so that's 1/2 of arcsecant t over 2 plus c, or d. Any questions on this one? Oops. Okay, so I'm going to end with one of these. We'll end with this one.